Okay. Yeah. Devendra, you think we should start now?
Just wait a minute, 1 minute, maybe some people will join after 3. Just 1 minute.
Yeah, sure.
This is already lecture 2. I thought this is first lecture.
No, yesterday I gave a lecture. This is lecture
you gave
2,
yesterday.
yeah, I had to change the dates and so on.
Professor Gadadhar Misra, maybe start to introduce. Professor Misra, are you there?
Yeah.
So take over.
Okay. All right. Yeah. So welcome everyone, and I'm sorry that I missed the lecture yesterday.
Somehow, maybe you turn around actually.
Yeah, actually, because the camera is behind you. Yeah. But why is that? I mean, you have a computer at this end and the screen at the other end.
See, after all, Narayanan is the hero of this story. Let me not steal, whatever. So,
Steal my
anyway,
thunder, yeah.
to the second lecture by Professor Narayanan, and I wish I was there yesterday, but I have now sort of talked to him, checking and learning what he did in the first lecture, and so hopefully we will be able to catch up, and those of you who are there will of course continue and have a good time. So let me welcome Narayanan to give his second lecture in this series. Thank you. Narayanan?
Okay, thank you very much. So we'll continue. So let me do a quick recap of what we covered yesterday. So remember that G is SL2R. Okay. And K is a maximal compact subgroup, which we can identify with SO2. And if I take a representation by V, so we will always assume this to be unitary, although whatever I say works for one-arc space representations. We will assume it to be unitary. We defined V sub n's. So these are spaces, these are vectors in V which transform according to representations of K. Okay, so this is all those V in V such that pi of k theta. So remember k theta, I'll write it down. V equal to e to the in theta V. Okay, so what was k theta? K theta was our matrix cos theta minus sin theta cos theta. Right, that is the standard matrix in SO2. Yeah. Okay. And well, because we are on a Hilbert space and so on, these Vn's are orthogonal to Vm if n is not equal to m. And we also know that V is actually the Hilbert space direct sum of these Vn's. Okay. Of course, some of the Vn's may be 0. Okay, we don't know which Vn's survive, but there are some Vn's which will, of course, survive. Okay, then we defined the C infinity vectors. So let me remind you, C infinity vectors. So if I take a vector V in V, it is called C infinity if the map x going to pi xv is C infinity, right? So this is a map from the group G to the Hilbert space V, right? And then we saw how to construct C infinity vectors, right? So if I take f in CC infinity of G, smooth function with compact support on G, I can define pi of f. This is the Fourier transform of f, if you like. That is integral over G, fg dg, fg pi g dg. In whatever sense you want to make this an operator, and since it's unitary and all that, you can take the norm inside. You see that it converges nicely. So it's a bounded operator on V. And if f is C infinity, you see that pi f V is a C infinity vector. Okay, and C infinity vectors are denoted by V super infinity. And if I take a C infinity approximate identity, then it is easy to show that pi f and V converges to V as n goes to infinity, which means that C infinity vectors are dense. Okay, so this is sitting inside, so it's obviously a subspace, and it is sitting inside as in the whole Hilbert says as a dense subspace. Okay, all right. So that's where we are. And then we differentiated the representation to get a representation of the Lie algebra, right? So recall that if I have pi, we defined, so for x in the Lie algebra G, so Lie algebra G is simply trace zero matrices. For x in G, we defined pi dot of x, right? That is just to distinguish between the representation of G and representation of Lie algebra. So this acting on a C infinity vector V is d by dt at t equal to 0, pi of x dx acting on V. Okay, so V is a C infinity vector, so that this is differentiable, right? So t going to pi of x dx acting on V is a differentiable function if V is a C infinity vector, and derivative of that is pi dot. Okay. So the pi dot exists. So if you want to think of pi of x dx as a unitary one parameter unitary loop, then pi dot exists using Stone's theorem, if you like. And the important point for us is that pi dot of x bracket y is pi dot of x, pi dot of y minus pi dot of y, pi dot of x. In other words, pi dot is a Lie algebra representation. Okay, on the space V infinity. See, Lie algebra does not have any topology and things like that. This is a purely algebraic concept. Okay, so you have a linear map pi dot from G to linear maps on V infinity. V infinity is a vector subspace, and you have the pi dot respects the Lie algebra operations. Okay. So in other words, so in the module language, V infinity is a G module. Okay, so there is a Lie algebra action on V infinity. So that is where we are. So we continue. So it's not enough to look at the Lie algebra. You can apply the Lie algebra element as many times as you want. Okay, so each element in the Lie algebra is like a left invariant differential operator on G, and you can look at higher differential operator. Okay, so that's what leads us to universal enveloping algebra, and we will denote it by U of GC. Okay, so GC is the complexification of G. So GC equal to G direct sum IG. So here it's okay because G direct sum G and IG are, so G and IG you think of sitting inside 2 by 2 complex matrices, and they are disjoint, so you can make the direct sum. So you will get SL2C. Okay, so small SL2C, right? And so you look at GC, and then so universal enveloping algebra UGC is defined to be, so the algebraic definition is the tensor algebra of GC quotiented with a two-sided ideal. Okay, so X tensor Y minus Y tensor X minus X bracket Y. Okay, what is TGC? So TGC is GC plus C plus GC, some GC tensor GC, etc. Right, that is a full tensor algebra. Okay, we will not get into too much details about this. What is important from our point of view is that UGC, the universal enveloping algebra, can be identified as left invariant differential operators on G. All left invariant differential operators on G. Okay, so if x1, x2, x3 is a basis for GC because it's three-dimensional, but these are all general facts. Okay, you can take, depending on the dimension of GC, you take that many vectors and you basis for GC over C. Then the monomials. So this is an ordered basis, right? I'm telling you what is x1, what is x2, and so on, right? So there is a first one, second element, and so on. And you use the same order to make monomials. So then the monomials, x1 to the j1, x2 to the j2, etc. So there are only three here I have written. So x3 to the j3. Okay. So this collection, j1, j2, j3, j1, j2, j3 in n and union 0, if you like. So this is a basis for UGC. Okay, so is a basis for the universal enveloping algebra. Okay, so that is how. So this is called the Poincaré-Birkhoff theorem. Okay. But as I said, from our point of view, it is easier to think of them as left invariant differential operators. So let's do that. So let me tell you how it is identified. So if f is a smooth function, and I take a Lie algebra element, I want to view it as a left invariant differential operator acting on such functions f, right? So define. So so just to distinguish between x and the differential operator, let us look at x tilde acting on the function f. So I'm going to differentiate f in the direction of the Lie algebra element x. Okay, so I should tell you what this is at some point x, right? So that is simply d by dt at t equal to 0, f of x tx, right? So x tx, remember, is in the group G. And the way it is defined, if I put some group element on the left of x, that is same as putting the group element here. In other words, the differentiation commutes with putting elements on the left, right? So these are left invariant differential operators. So left invariant vector fields, first order differential operators, right? And then you can form higher order differential operators by acting these things again and again. Okay, so starting with the Lie algebra G, you get all these first order differential operators, and then you can generate the whole algebra of left invariant differential operators on the group G, right? Or meaning on which will act on smooth functions on G, and UGC can be identified with that. Okay, so the universal enveloping algebra is actually equal to meaning it can be identified all left invariant differential operators on, let's say, C infinity of G. Okay. Instead of saying on G, let's say on C infinity. Okay, they act on C infinity. Now, what is the advantage of having some huge? So this is a huge object. Okay, it's infinite dimensional, right? You're looking at all different. So, for example, on Rn, left invariant differential operators will be partial differential operators with a constant coefficient, and that's an infinite dimensional space, right? So UGC is a huge object compared to G. G sits inside UGC, of course. So I have C, which are constant. So these are identity times something, and then I have the Lie algebra G, which acts as first invariant differential operator, left invariant vector fields. So they sit inside UGC. Now, the point of this is that if I have a Lie algebra representation, it extends to a representation of UGC. So UGC also has a bracket operation. Okay, so if I take D and F, two differential operators in UGC, then this would make sense, df minus ft. Okay, that makes sense because d times f meaning it's a composition, right? So it's a differential operator followed with another differential operator. Okay, so the important proposition for us is if script A is a complex associative algebra with identity and phi from G to script A is linear such that P of xy bracket xy is phi x phi y. Phi x phi y makes sense because these are in A and A is an algebra, so there is a multiplication phi y phi x. Then there exists a unique associative algebra homomorphism phi tilde from UGC to A, which extends phi. So in other words, any Lie algebra representation to an appropriate space, right? So script A is a complex associative algebra with identity, blah, blah, blah. You can forget all that. Think about linear maps on a vector space, okay? So if I have a Lie algebra representation, then it extends to a representation of the universal enveloping algebra, okay? So this is all I'm saying there, okay? So, but this is the exact statement. So as a corollary, so recall that if I have a representation by V of G, then I have a representation pi dot V infinity of the Lie algebra, right? So this will extend to a representation which we will call pi dot again of UGC, right? Because the Lie algebra representation of so Lie algebra representation extends to a representation of UGC by this proposition. So in other words, V infinity is a UGC module. Okay, so this is where we are now. So we started with a unitary representation of G, differentiated it, got a representation of the Lie algebra, extended it to a representation of the universal enveloping algebra. Okay, so that gives us a lot more operators to act on our space. So we need well, we'll see that it's not enough to look at V infinity. We need to look at what are known as analytic vectors. But let's see if I need it now. Okay, so let's look at some result on unitary irreducible representation. So recall that our aim is to classify unitary irreducible representations of SL2R and then see if we can prove Plancherel theorem, right, following Harish-Chandra. Any questions? Yeah, okay. So let's prove a theorem. Okay, so so let's see if I need. Okay, so we'll prove it. Let phi V be a unitary irreducible representation of G. So G, remember, is SL2R. And recall that we define these Vn's, right? These are vectors which transform according to the nth character of the circle group. So these are all V here such that pi of k theta V equal to e to the in theta V, right? So these are our Vn's. So it is unitary and irreducible. Okay, that is important. Then dimension of Vn. So this is in general, this is a very important theorem due to Harish-Chandra. For SL2R, the proof is much simpler. Okay, so dimension of Vn is less than or equal to. So if Vn survives, then there is a single vector there, right? Essentially. So dimension of Vn is 1. Of course, some of the Vn's need not survive. Okay, so Vn's can be 0. Okay, so we will prove this. Okay, so when I say we prove this, we go through the steps which are important. So step 1.
Did we assume in the beginning that V is separable?
Well, all Hilbert spaces are complex and separable. Okay, so we are not looking at anything other than that. So step 1, define CCG. So G is SL2R, CCG is all continuous functions with compact support. So I'm going to put subscripts N and M here, okay, to denote this will be the collection of all those functions which transform according to nth character of K on the left and mth character of K on the right. Okay, so it's a bit cumbersome and slightly technical. So this is F, all continuous functions with compact support, and F of, so I take a K theta X, let's say K phi, okay. So on the left, if I hit by K, the nth character will come out, but I put a minus n, okay. So F by e to the minus n theta, F of X, e to the minus m phi, okay. Okay, all these are scalars, okay, so they all commute. I can write anywhere I want. I just write it like this so that it's clear that m comes on the right side, n comes on the left side. Okay. Then the usual Fourier series steps will show you that. Then the algebraic direct sum, and NM CCG NM is dense in CC. Okay, that's the usual Fourier series approximation in the L1 norm. Okay, so I should also say that in the L1 norm. You can also use the supremum norm if you want, appropriately convolving with the fair kernel and so on. Okay, so that is one. So this is decomposing. So think of the K action from the left and the right, and then you take the Fourier series, right? So decomposing with respect to the K action. Okay. So that is one. Step 2. What happens to convolution of these pieces? Okay, so CCG. So I'll put one here. CCG n comma m convolve with CCG L comma Q. Okay, so I'm taking two such pieces, right? If I convolve them, so this is going to be 0 if m not equal to L. So m comes from here, right, on the right, and L comes from here on the left. Okay, so if they don't match, the convolution is 0. That's so these things are straightforward. Okay, you write down the convolution, put the K theta inside. Some of them will come out because the definition is like that, and they don't match, so you will get 0. Okay, and if they match, it will go inside CCG of n comma q. So if m equal to L, that means whatever is in the middle, right? M and L, they are equal. They will go to the whatever is at the end, n and q, right? If m equal to L. Okay, that's a straightforward exercise. 2. CCG n m star equal to CCG mn. M and n will get interchanged. What is star here? The star operation is f star of x equal to f of x inverse bar, right? That is the usual the adjoint action on L1, right? L1 of G. Okay, it's unimodular, so there is no modular function that gets multiplied. And third one is very particular to SL2R. It's not true in general if you go to other semisimple groups with finite center. CCG, so this is one of the steps which makes our proof simpler. NN. So when I take both N, this is commutative. Commutative with respect to the convolution. Okay, so this is true only for SL2R. Because for other groups, the representations of K can be higher dimension. Okay. Here it is one dimensional, so that makes it a bit easier. Okay. So under convolution, and it's true for SL2. Okay, so again, all these are straightforward. Only the third one requires a bit of a work, but that is if you have seen something called Gelfand trick in proving something is a Gelfand pair. Something is a Gelfand pair, meaning some convolution algebra is commutative. It's essentially the same trick. Okay, so let's go to the next step. So step 3. Again, 1. So Vn is orthogonal to Vm. Remember Vn and Vm, these are vectors which transform according to the nth character and mth character of K. Of course, they are orthogonal to each other because you are in the Hilbert space, and these are different characters. So that is trivial. 2. So one of them we will prove just to convince ourselves that everything is fine. So CCG. So remember, if I have a representation, I can extend it to CCG, right, or L1G by integrating, right? So CCG, NM. So remember, these are compactly supported functions which have that transformation property. Pi of that would mean pi of f, where f comes from that algebra, right, or that space. Acting on V will go inside Vn. Okay, so you should be careful about where the n is. Okay, n is on the left, right? So this n. Okay, and there is one more. So 3 pi of CCG NM acting on V sub q. So what is q? Q is again some integer. V sub q is all those vectors in V that transforms according to the qth character of K, right? That we had defined. And if I do this, then this will be 0 if q not equal to m. Okay, so if these two don't match, then I get 0. Similarly here, so here I'm taking the whole space V. Okay, and so remember, V is the direct sum of all these VQs. So when I apply, only certain things will survive and so on. Okay, so that is something you can keep in mind. So let's prove this just to convince ourselves that this is fine. Okay, so prove this. So I take a f in. So this is a simple, straightforward computation. So CCGNM. Okay, and I want to know what happens to pi f v, right, where v is a arbitrary vector from our Hilbert space V. I want to know if it is in a certain space Vn, right? Question is whether this belongs to Vn, right? Which means I should apply K to it and see what character comes out, right? So I apply pi k theta to pi f v. Pi f v is integral over G f of x pi x v dx. Okay. So this is equal to, so pi k theta will go inside and then this will get combined with this, right? But remember, pi is a homomorphism. So that is G f of x pi of k theta pi x v dx. Sorry, this is a homomorphism, so I can write it as so that is pi of k theta x v dx. Now I can change k theta x to x, right? So I am putting, which means I am putting x to be equal to, let's say x equal to k theta inverse y, right? And her measure is invariant. So this will become the k theta comes with f, but with an inverse x pi of x v dx. But then f comes from this space, right? And so that n should come out. So this is nothing but e to the in theta f of x, right? So this will be e to the in theta into pi f v. And so pi f v will be in the correct space in Vn, right? That is what we wanted to. Okay, and similarly the other one. Okay, I'm not going to do that computation again. So what we are doing is we can decompose the whole Hilbert space into VNs. Similarly, you can decompose CCG into these smaller pieces using Fourier series. And when you apply only some of them, so if I apply CCG to this decomposition of V, they will apply only on certain pieces. Other pieces go to 0. Okay, so now we go to step 4. If phi V is irreducible, then, so this is important, then VQ is irreducible for pi of CCG QQ. Okay. So that is the important step, because CCG QQ, remember CCG NN is commutative. So what you have is a commutative algebra which is closed under the star operation, acting irreducibly on a subspace. Then it has to be one-dimensional by Schurzlem, right? So that will prove that our space is one-dimensional. So let us prove this. So this requires some work. So proof, and we need all those cumbersome steps where all those CCG and M acting on V. How does it look like? Okay, so let's keep a picture in mind, so our V is a direct sum of VNs, right? So I have one box, another box, and so on, right? All these are, think of them as VNs, okay? Vn plus 1 and so on, okay? Like this. And they are all orthogonal to each other. So it's a direct sum of various spaces, right? One of them is VQ. Okay, so let's think of VQ as a bigger box here. Okay, I want to say if phi V is irreducible, then VQ is irreducible for this algebra, right? This space. So let us start with a W which is smaller than VQ and invariant under this. Okay, so let W contained in VQ. So of course, we always look at only closed subspaces which are invariant, right? So W contained in VQ be closed, be invariant for pi of CCG QQ. Okay, that means I take any function from, so that is pi f W will be in W if W is in W and F is in CCGQ, right? That is what we mean. Okay. Now we apply all the previous results we have about how all these smaller pieces, CCG and M's, apply on V, right? So let us recall that. So we see that there are a couple of things here, right? So I have this portion in the lemma and this, right? So if the M and the Q do not match, then I get 0, right? And whatever arbitrary vector I take here, I will go inside Vn as long as the left-hand side here is n. Okay. Now, if I look at, so I want to justify the following statements. Okay, so if F is a finite sum, so let's write F equal to F n m finite. So F is in CCG, okay, and F n m is in CCG in the corresponding space nm, right? On the left, it's you get an e to the minus I n theta. On the right, you get an e to the minus m phi, right? And I take W in W. So remember, W is the smaller space than VQ, which is invariant under all functions coming from a certain space, right? So W in W. Then the qth component of phi f W is equal to phi of f QQ of W, and that will be in W. Okay. Right. So why is this? This is because I am applying. So remember this finite sum. F is of this finite sum, and W comes from, so W is in W. So this is contained in VQ, right? So that comes from the qth piece. So unless this matches with Q, it will not survive, right? So the second index has to be Q, right? And the first index Fn decides where it goes, right? So let us see. Yeah. So the first index decides where you land, right, in Vn. So if I want the qth component, then both n and m should be q. Otherwise, you are not going to get the qth component. You will go elsewhere, right? Sorry. So the qth component of such a vector has to come from the qth piece of your f. Okay, that is the only way. Okay, but you see, W is invariant under CGQQ, right? And so since I'm taking finite sums, and I can take approximate, because this is dense in L1 with respect to, right, dense in CCG with respect to the L1 norm. So by denseness, it follows that pi f W will be in W for every f in CCG. Okay, because any function f in CCG is a sum of these f and m's, right? And for each such finite sum, you are landing inside W, right? But then this is a contradiction, because if I so what is the contradiction? I'm starting with an irreducible representation. So it is irreducible. So if I start with an irreducible representation pi v, it is irreducible for CCG as well, right? That was one of the first things we did. But we are getting a smaller subspace where everything is invariant. Okay, so this is a contradiction. Okay, so because of that, so that proves that if pi v is irreducible, then each component VQ is irreducible under the qth component of CCG. Okay, so now we can complete the proof. So that is the last step. Step 4. Let pi be unitary and irreducible. Then what we have proved is each Vn is irreducible. Each Vn is irreducible for pi of CCG NN, right? That is what we just proved. Okay, but see, pi of CCG NN, so pi of CCG NN is commutative. Because under product, right? Because CCG NN is commutative with respect to the convolution, right? So CCG NN is commutative with respect to convolution, right? So pi of that is going to be commutative, right? These are going to be operators, and also commutative and closed under adjoints, closed under star, right? Because CCG and star is itself, right? Remember, the star operation is just f of x inverse whole bar, right? So this becomes a self-adjoint algebra of operators, right? Closed under star operation, and it is acting irreducibly on it's a commutative self-adjoint algebra acting on a Hilbert space irreducibly. So that space will have to be one-dimensional by Schur's lemma. Okay, so hence by Schur's lemma, I mean, if of course it can be 0, right? So dimension of Vn equal to 1 if it is not 0. If it is not 0. Okay, so this is the major theorem. It is made simple because we have this commutativity of CCG NN. Okay, that is why it becomes one dimensional. In general, you have, so instead of Vn, you will look at representations of K. So maximal compact K need not be abelian. It can be a complicated compact group, but you know that the representations, unitary reducible representations, are finite dimensional. And one can, so Harish-Chandra's theorem is that the corresponding space, so for each, so if I take a representation of G, I can define V delta for delta in K hat, right? So you look at the maximal compact K, look at all its irreducible unitary representations, take one delta and look at V sub delta, that is like V sub n. These are going to be vectors which transform according to the delta representation of K. Then the V delta is, the dimension of V delta is less than or equal to degree of delta square. Okay, they are going to be finite dimensional if pi v is unitary irreducible. And then one defines what are known as admissible representations, which can be Banach space representations, where these V deltas are actually finite dimensional. And the infinitesimal method essentially characterizes such representations. Okay, so the method characterizes all Banach space representations for which all these V deltas are finite dimensional. Okay, so in our case, all the Vn's are finite dimensional. So when you have a Banach space representation, all that we can say is Vn's are finite dimensional. Okay, those are the admissible representation. But when it is unitary and irreducible, then the Vn's are dimension 1 if they exist. Okay, otherwise 0. Okay, so now, so this is a major result. So now we can define analytic vectors. So I'll not do anything with analytic vectors today. I will do that in the next class. So our aim is to define analytic vectors. So remember, we defined C infinity vectors. And analytic vectors are, of course, going to be smaller than this. Analytic vectors. And we will see that. So remember, the C infinity vectors is a UGC module. Okay. And the same thing will happen with analytic vectors. Okay. And then we will see that the what are known as K finite vectors, they are sitting inside analytic vectors, and this is also a UGC module. Okay, so what are K finite vectors? These are essentially the algebraic direct sum of Vn's. Okay, so you look at finite Fourier series essentially, right? So these are your K finite vectors, and the correspondence is that if I have a unitary irreducible representation, you look at the corresponding K finite vectors as a UGC module. Okay, so that gives me a correspondence between. So you look at invariant subspaces in the K finite vectors with respect to the UGC action. They are same as invariant. So if you take the closure of them, you will get invariant subspaces under G in the original Hilbert space V. Okay, so irreducibility would mean that it is irreducible at both levels, at the Lie algebra level or the UGC level, as a representation on the K finite vectors, and the Lie group level as a representation on the Hilbert space. So these are going to be same. Then we can look at the K finite vectors and look at its structure. In our case, remember, the dimension of these Vn's are going to be 1 if they exist. So there is only one vector. So it's a very simple space where each space Vn is spanned by a single vector. So you look at which ends appear, and there is a certain eigenvalue for the Casimir, and these two will characterize our representation. Okay, so it is quite simple to understand in the case of SL2R, but as you go to other groups, it gets complicated. So as a first step, we'll define analytic vector. So I will not prove anything except writing down something. Okay, so let's define analytic.
Do some Vn's get lost in K finite? So is it
Yeah, so all
dense?
the Vn's need not appear. We don't know which Vn's appear.
Okay.
Some Vn's will appear. Okay, so I mean, we started with that, right? So this is a decomposition which we know exists, but we don't know which Vn's appear there. Okay. So once we start analyzing, we will realize that the ends that appear have a certain structure. So
No,
it has to be
relative to C infinity vectors.
Yeah.
The collection of n's gets smaller, right? From C infinity to analytic to K finite. That's my
No,
question.
no, no. So all the okay. So maybe I should let me write it in a slightly better way. So all of them. So algebraic direct sum of Vn's. They are all analytic vectors. And all the analytic vectors are, of course, C infinity vectors. Okay, let me define analytic vectors. So, phi V be a representation of G. V in V is said to be analytic. Analytic if x going to pi xv is analytic. Is an analytic function. Is analytic. Okay. So of course, for analyticity, weak analyticity, strong analyticity, everything is same. So let me recall that f from G to V is analytic if you compose it with a linear functional. If x going to alpha of f of x, where alpha and V star is analytic, that will do. Okay. So weakly analytic and strongly analytic, these are all same. When you look at analytic function, that is one advantage. So analytic vectors are, of course, because x going to pi xv is analytic, so in particular it is C infinity, so they are C infinity vectors. The result we would want to we will prove is that any k finite vector, that means whatever is there in the algebraic direct sum of Vn's, that is going to be an analytic vector. A priori, it is not clear that they are even C infinity, right? It transforms according to certain representations of K, that is all. But we will prove that they are actually analytic vectors, so that is strong. And this space of analytic vectors, there is a UGC action. Okay, so that means the universal analytic algebra acts on it, which means if I differentiate a analytic K finite vector, I'm going to get a K finite vector. So that gives me a modular action of UGC on the algebraic direct sum of Vn. Okay, purely algebraic state. But then that is enough to characterize our representation. Okay. So, yeah. So yeah, I'll stop with just some more definitions perhaps. So V omega. So this is called this is the notation for analytic vectors in V. Of course, V omega is sitting inside V infinity, that we know. So the V omega is also invariant under, so also a UGC module. Okay. If V is in V omega, then one can actually expand, right? Pi of x V equal to summation n equal to 0 to infinity pi dot of x n divided by n factorial V. Okay, so that is how you will expand. So this is simply expand t going to pi of x dx acting on V at t equal to 0. Right? Yeah, all right. So yeah, I won't prove that this is a UGC. It's not very difficult. So just like C infinity functions, if you differentiate a real analytic function, you are going to get a real analytic function. Okay, so that's what essentially this means. So the result which connects invariant subspaces under the Lie algebra action or the universal enveloping algebra action and the group action. Okay, so that is the correspondence we want. Okay, so let us write down that. So this correspondence apparently is not true for C infinity vectors. So that's why one needs to go to a smaller subspace. So let pi V be a unitary representation of G. Let W contained in V omega. So we are looking at analytic vectors and look at a W which is be a subspace. be a subspace invariant under pi dot x in G. Okay, and so it will be invariant under the UGC action, right? So my G is then W bar. So here this is a subspace. I'm not saying it is a closed subspace. Okay, so V omega. Well, we don't know right now. We don't know V omega exists or not. Okay, there may not be any analytic vector. How do we know? Okay, once we prove that k finite vectors are analytic vectors, k finite vectors are actually dense, right? Because the orthogonal direct sum of Vn's is the whole space, which means that algebraic direct sum is dense in the whole space. So once you prove that these algebraic direct sum of Vn's are actually analytic vectors, then they are actually going to be dense, right? So the analytic vectors will finally see that it is actually a dense subspace. Okay, but that is something we have to prove. Right now, we don't know if they exist. You can construct by hand, but that we will not get into. Then the closure of W is an invariant subspace for the G action. Okay, so for pi G in G, right? So this is easy. So this is a one-line proof. If W in W and X in G in the Lie algebra in a small neighborhood of 0, then you have the power series expansion. So pi of x specs V equal to summation n equal to 0 to infinity pi dot of x to the n factorial V, and of course this will be in W bar, right? Because each of them is in W, right? Because it is W is invariant under pi dot of x for every x, right? So you can apply it as many times as you want. You will still be in W. So all of them are in W, but you are doing an infinite sum, so it will be in W closure, right? And if I have small neighborhood from G, which leaves W closure invariant, then all of G will leave W closure invariant, because a small neighborhood generates the whole G, right? So complete the proof using the fact that small neighborhood of identity in G generates G. Right? That's true for any connected topological group. Okay. So that gives us a one-way direction. So this is only going from UGC module to, or invariant subspaces for UGC to invariant subspaces for G, right? We'll give a one-one correspondence between those two, but not with analytic vectors, with k finite. Okay. So I think I'll stop here for the time being. In the next class, we will see why k finite vectors are analytic vectors. So there we have to bring in certain Lie algebra elements and an elliptic operator. So we'll have to use the elliptic regularity theorem at some point, which I will state. Yeah. Okay. So I'll stop.
Yeah. Thank you, Narayanan. That was nice recalling the first lecture, and yeah. So your next lecture is when?
Next week, I think next Wednesday.
6th
Yeah,
Wednesday.
6th. Yeah.
So are there any questions that you have for Narayanan? Anyone? Yeah. So yeah. I guess we'll then meet next week for the third lecture in this series, and let's thank Narayanan for his lecture today.
Thanks, Professor Misra, also for coming to chair and booking a classroom also.
Yes, yeah.
Okay, all right.
Okay, see, we will close the meeting now.
Right.
Yeah.
Okay.
Thanks.
Thanks.
Okay, thank you. See you next week. Yeah.
Right. See you next week. Right. Bye.